In the snow-covered wilderness of Czech Republic, researchers recorded a red fox diving into the snow and emerging seconds later with prey it never saw, never heard. This shouldn't be possible. 3 feet of thick snow blocks all clues, no visual cues, sound waves scatter, scent trails disappear. Yet the fox attacked with a precision as if it could see beneath the snow. Dr. Jaroslav Červený from the Czech University of Life Sciences describes this as a success contrary to predator biology. Wolves rely on hunting in packs, bears on raw strength and their sense of smell. But what about the red fox? It aligns its body with Earth's magnetic field. And when senses like hearing or smell don't work, it attacks its prey blindly with remarkable accuracy. Tonight we'll discover how the red fox became nature's only magnetic hunter and how this ability remained hidden from science until 2011. If this mysterious hunting ability impressed you as much as it did me, like and subscribe. In the comments, write where you're watching from, what time it is there, and what surprised you most about the red fox. You're the reason we keep discovering nature's secrets. Thank you for being here. First, let's note that researchers don't entirely agree on the findings we're about to discuss. Some information isn't certain. Now let's slowly begin to discover the secrets behind the red fox's extraordinary hunting ability. A red fox stands motionless in a meadow in the Czech countryside. The surroundings are covered with snow. In some places, the snow is 3 feet deep. Beneath that frozen blanket, a mouse moves through tunnels between the ground and the snow. The mouse thinks it's safe. No predator can see it, can't smell it from under all that snow. Naturally, the mouse should survive, but something unexpected happens. The fox tilts its head slowly, as if it's found its target. Its ears rotate independently to pick up sounds we can't hear. It takes one step, then another step. The movements are calculated, almost flawless, and then suddenly the fox launches itself upward. It rises so high without all 4 paws touching the ground. Taking a soft arc in the air, it dives headfirst into the snow. When it emerges a few seconds later, a mouse hangs from its mouth. That's it. With a single strike. This hunting technique has a name. Biologists call it mousing. But this name doesn't explain the mystery. How did the fox know where to strike? It can't hear the mouse because snow absorbs sound waves. Seeing is impossible. Scent trails are lost beneath feet of snow. We've been observing this behavior for decades. Hunters and naturalists have documented it in various parts of Europe, North America, and Asia. Until this time, we thought the fox used hearing to locate prey that's hard to see. Because, despite the snow, the fox's ears were good enough to detect its prey with perfect precision. But this assumption was wrong. The truth was a bit different than we thought. Dr. Jaroslav Červený noticed something unusual was happening. He formed a team of 23 hunters and wildlife biologists. Their task seemed simple at first: to observe how foxes hunt in winter conditions, to record every jump, to document every success and failure. But Červený wasn't just interested in success rates. He wanted to learn exactly how the fox did this. The team spread across the meadows and fields of the Czech Republic. Between 2008 and 2010, they observed 84 foxes in different habitats at different hours. The team witnessed hundreds of hunting moments. Then, when they looked at the data, a picture emerged that couldn't be explained according to traditional predator biology. Foxes weren't jumping randomly, they were jumping in one specific direction, northeast, roughly 20 degrees off from magnetic north. Think about this. You're a fox standing in a snow-covered field. Your prey could be anywhere around you in any direction: north, south, east, west. Dr. Cherveny's team saw that foxes stopped and listened to their surroundings before attacking, as if they were trying to catch the sound. But if you're only using hearing, hunting in every direction would be equally successful, because sound doesn't care about compass directions. But these foxes predominantly chose to attack toward the northeast. 73% of attacks in this direction were successful. This shows they're not using hearing for hunting, and their attacking northeast isn't coincidence. Attacks in the exact opposite direction, southwest, had a 60% success rate. In other directions, there were only 18% successful attacks. This isn't random variation, this isn't chance. This shows that a fox is detecting information we don't know about. Cherveny's team considered every possible explanation. Maybe foxes were using environmental cues. Maybe wind direction was important, or the time of day, or the position of the sun. They controlled for every variable. The result revealed something unexpected. The direction of attacks was independent of the time of day, the season of the year, and wind direction. Foxes were orienting according to something unchanging, something like Earth's magnetic field. This is where it gets interesting. The ability to sense magnetic fields may be more common among animals than we thought. We know that birds use it for navigation during migration. Sea turtles use it to return to their nests. So this ability isn't unique to foxes, but how they use it matters. All the other animals we've studied use magnetic sense to find direction, to determine their location. Birds know which direction is south, but the fox isn't finding direction. It's hunting. Researchers haven't yet found exactly what the fox uses the magnetic field for, but we think they might be using it like a ruler to measure the distance to their prey. So is the magnetic field sufficient for this? Here's the theory. The fox moves slowly, surveys the surroundings, listens to sounds. As it picks up the sound, it orients more toward the target point. It moves forward until it can make an estimation. When the angle of the incoming sound aligns with Earth's magnetic field, the fox estimates what distance it is from its prey. Not too close, not too far. The distance needed for the jumping motion to reach the target. If the theory is correct, the red fox would be the first animal to use the magnetic field as an aid in hunting. Professor Heineck Berder, in the study conducted with Cherveny, thinks the fox might actually be able to see the magnetic field. Really, it might actually see it as a visual layer embedded in the landscape around it, just like the heads-up display in video games. Here's one thing that supports this. Research has found proteins in foxes' eyes that respond to magnetic fields. Professor Berder suggests that a shadow appears toward magnetic north in the fox's eye. Imagine this. A fox first hears the sound of its prey. As it moves forward, it notices a shadow appearing before its eyes. When the source of that sound aligns perfectly with that shadow, it jumps. It doesn't need to think about how far away the prey is. Its brain does this automatically based on that visual and magnetic alignment. We don't know for certain whether foxes experience this. We haven't yet found the specific cellular structures that enable magnetic sensing in foxes, but the behavioral data is undeniable. Foxes hunt more successfully when they orient their attacks in magnetic northeast. The difference in success rate is too large to ignore. In each of hundreds of observations, too consistent to be coincidence. But one thing isn't entirely clear. If magnetic hunting is this effective, why don't foxes always use it? Why do they only use it in snow or tall vegetation cover? The answer reveals something fundamental about how this system works. When prey is visible, the fox doesn't need magnetic alignment. Because the fox's eyes are sufficient for this, they don't need other senses to determine direction. But when visibility drops to zero, the fox uses magnetic sensing. The reason for this is that when prey is under snow, the fox can't combine visual cues with its hearing. Field observations confirm this. In areas covered with short grass or shallow snow, when prey is partially visible, foxes show no directional preference. They attack from any direction with almost equal frequency. This shows that magnetic sense isn't the fox's primary hunting tool. It's a backup system for the special challenge of hunting under deep snow and dense vegetation. And this adaptation is a feature that sets foxes apart from all the other terrestrial predators we've studied. You know wolves, they hunt in packs using coordination to hunt large prey. They don't have to hunt under snow. Their prey is large enough to be visible even in winter conditions. Other predators that rely on auditory cues to find their prey have developed special mechanisms to increase hunting accuracy. But foxes focus on small and invisible prey, and they're not large enough to hunt this prey alone. Foxes had developed a different solution to this problem. However, magnetic sense, no matter how remarkable, only works in the wild, in the forests and meadows that have shaped them for thousands of years. When foxes began settling in cities a century ago, they entered environments where none of these hunting abilities should provide an advantage. Sidewalks replaced snow, discarded food replaced mice. Yet urban fox populations grew rapidly. They didn't just survive in cities, they thrived in ways that left forest populations behind. London now hosts more foxes than many wildlife habitats. Berlin, Tokyo, Los Angeles all host urban fox populations that shouldn't exist according to what we know about the wild. So what happened to the magnetic hunter when it encountered crowded cities? Chapter 2. Cities make everything evolution designed for foxes to use more difficult. Yet foxes have found ways to survive in this complex world. Street lamps fill the darkness with artificial light. Pavement replaces snow and soil. But when we examine London today, we encounter a situation that questions what we know about fox ecology. 24 foxes per square mile, the population density measured by researchers in the suburbs of Brighton. For comparison, the best wildlife habitats in England's rural areas hold approximately 4 to 8 foxes per square mile. Cities aren't just hosting foxes, they're supporting populations 3 times denser than the best natural habitats. In recent years, urban areas are increasing worldwide, and this change is also affecting wildlife. Red foxes in particular are increasingly preferring cities. When foxes encountered urban environments, a fundamental change occurred, and this change happened faster than nature is used to. The first urban fox observation in England was made around 1930, a single fox seen in a neighbourhood of London. An anomaly, an unusual thing, but not particularly noteworthy. Nature experts assumed it was a rural fox lost from a very distant area. It would either leave or die. Cities were dead zones for wildlife. Everyone knew that. But the fox didn't leave and didn't die. Within 20 years, reports from other English cities started coming in. Bristol, Manchester, Birmingham. By 1995, researchers estimated that England hosted 33,000 urban foxes. Today, this number is significantly higher because foxes have colonized almost every town and city in the United Kingdom. This seems to contradict the rules of nature. Think about what a city offers compared to the wild. No meadows full of mice, no forests with rabbit burrows, no natural shelter except parks and gardens. Traffic kills animals every day, noise that would disrupt sensitive hearing ability, lights that eliminate the darkness that night hunters need, people everywhere. This is a list of obstacles that should make survival in the city impossible for a wild predator. But these obstacles didn't matter. The fox found something in our cities that we weren't aware of: food, shelter, and, surprisingly, safety. So how? They find food from gardens and trash cans. They use parks for hiding, especially when they're active at night. The trees and bushes of empty parks are perfect shelters. But the territory of a fox living in the city is smaller than that of one in the forest. This is normal. If you live in a city with plenty of foxes, your trash can become a buffet. The pizza you threw out last night? A fox finds it within a few hours. Discarded hamburger, chicken bones, meals you couldn't finish. We produce thousands of tons of edible waste in every city every day. For a fox, this isn't garbage. This is an opportunity. An endless food source without needing to hunt. No using the magnetic field. No diving into snow. Just open the box, or if it's closed, make it tip over and eat. Researchers studying urban fox diets found something unexpected. Despite having constant access to human food waste, urban foxes still continue to consume their natural prey. Squirrels, birds, and insects make up most of their diet. They hunt more comfortably because there are no competing predators in the city. Observations showed that urban foxes consume, on average, half of their nutrition from human-sourced food sources. So despite moving to the city, they haven't forgotten their old wild habits. But food adaptation is deeper than we initially understood. Your compost bin attracts worms and insects. Those insects attract mice and rats. Those rodents attract foxes. Without realizing it, we've created predator-prey ecosystems in our backyards. The fox isn't just feeding on dead animals, it's also hunting the animals our garbage attracts. Our trash, without us being aware, has formed the foundation of a food web in a city. And cities offer something the wild never provides: consistent shelter. The territories of urban foxes become smaller than those of forest foxes. Foxes living in the forest live in natural dens or under fallen trees. Finding good den sites is difficult. There's intense competition for quality areas. They're in constant migration. But in cities, they choose a permanent settlement and they live more in family groups. We build shelters for foxes that we don't intentionally make for them. Under your garden shed, under that abandoned car, the gap between buildings, behind piled wood, the narrow spaces under your homes. Every city hosts thousands of perfect den areas that stay warm in winter and cool in summer. Foxes adapted to city life very quickly. Until the 1980s, foxes in urban areas were mostly reported from the United Kingdom, but since 1985, they've also been frequently seen in cities of Canada, Australia, Germany, and many other countries. A study tracked the den sites of urban foxes in Berlin. Researchers found that foxes used 273 different artificial structures as shelter. Garden sheds were first on the list, then spaces under buildings, then gaps in terrace walls. No den was in a natural underground burrow. Every fox in the study area was using human-made structures as shelter. We've inadvertently become like the fox's construction crew. But here's where urban adaptation becomes truly mysterious. Food and shelter explain survival. They don't explain the population density we observe. Rural areas also have food and shelter. Yet urban populations exceed wildlife populations by 3 to 4 times. Something else is happening in cities, something that provides urban foxes with an advantage beyond basic resources. The answer came from an unexpected research project. Scientists studying urban fox behaviors noticed something strange during morning rush hours. Foxes crossing streets weren't moving randomly, they were waiting, watching, and crossing in very specific opportunity windows. Traffic lights were creating predictable gaps in vehicle flow, and foxes learned to use these gaps with timing precision, as if they truly understood traffic flow. A research team in Tokyo wanted to document this behavior with extraordinary clarity. They placed cameras at an intersection where foxes regularly crossed. They recorded 83 crossing events over 6 months. 71 of these crossings occurred at red lights when vehicles had stopped. Foxes weren't just lucky, they were reading the rhythm of the city and adjusting their behavior to match it. This behavior requires extraordinary memory. In remembering food sources, foxes remember which trash can is full on which day, in which garden they can find food when. But this memory ability pales compared to the food remembering memory that a forest-dwelling animal displays. In our next video, we'll discover the forest's most perfect memory keeper, the red squirrel, who remembers every cache location flawlessly. But for now, let's return to the fox's greatest advantage in cities. The ability to read traffic lights is just one example. Advanced urban adaptations have been observed in other cities as well. For instance, in the city of Zurich, Switzerland, large populations have been seen with more than 20 foxes per square mile. According to area residents, foxes in the city are increasing year by year. They're achieving this through very good adaptation. But wait, foxes don't understand traffic lights. They don't know that red light means stop, green light means go. They're wild animals. Yet the data doesn't lie. These foxes were crossing during paused traffic, and this behavior was too regular to be explained by chance. So, what were they really doing? We think they're creatures that learn behavioral patterns. Even if they don't understand the lights, they're learning the behavioral pattern those lights create. Cars stop. Wait 30 seconds, cars move again. The fox doesn't need to know why the cars stopped. It just needs to remember this. When cars stop, there's a safe opportunity. And if you cross during that opportunity, it means you won't get hit. This is a mental adaptation ability we didn't expect from foxes. They're not just adapting their food or shelters, they're learning the temporal patterns of human activity and adjusting their behavior hourly to fit our schedules. Urban foxes in many cities show similar adaptations. Approximately half of all reported human-fox encounters have occurred between 6 in the evening and midnight. Foxes in London move more in the streets during the hours before midnight. Foxes in Los Angeles wait for midnight. Foxes in Tokyo emerge around 10 in the evening. They're learning their environments and responding with surprising precision according to our calendars. We use the same puzzles to compare the problem-solving abilities of urban foxes with forest foxes, food that had to be moved to access. Urban foxes were bolder when approaching objects. They were more willing to touch new objects. But here's the surprise, they weren't more successful at solving the puzzles. Boldness increased. But did innovation increase? What does this mean? Urban foxes have adapted their fear responses. They're less afraid of new objects because new objects in cities are usually harmless. There might be food inside that cardboard box. That plastic container might also be worth investigating. Forest foxes approach new objects extremely cautiously because in the wild, new things usually mean danger. But cities have trained urban foxes in a way where curiosity is more frequently rewarded. Yet this boldness creates new questions about what feeds adaptation. Learning? Do individual foxes figure out city life through trial and error? Or is something deeper happening? Are urban fox populations genetically diverging from rural populations? Researchers in Zurich conducted genetic analysis on urban and rural fox populations. In this research, they encountered early signs of changes in genes related to energy use and exploratory behaviors. The differences were subtle, but sufficient to show that cities were selecting for certain traits. Bolder foxes have better breeding chances in urban environments. Their genetics spread through the population. Within a few generations, the entire urban population becomes behaviorally different from rural foxes. Now, what we need to consider is this: what other interesting physical characteristics do foxes have outside of learning mechanisms we haven't yet detected? And this rapid learning ability is just the beginning. The fox's head holds other secrets, other engineering marvels. Now let's dive into the secrets that make it one of the most successful hunters of the Northern Hemisphere. Chapter 3. The urban fox survives through learning and adaptation. But foxes in the wild face challenges that cities never impose. At midnight, a fox hunting in pitch darkness needs to know where it's going. It needs to see the ground beneath its feet. So how does our fox navigate terrain we can barely see, even with flashlights? Two researchers in Finland set up infrared cameras across a forest clearing. They wanted to document nocturnal hunting behavior without artificial light interfering with natural conditions. What they captured on film shouldn't work according to basic physics. A red fox moving at full sprint through timber and undergrowth in conditions where human eyes register only blackness. Not cautious steps, not slow exploration, full speed, running with the confidence of an animal moving through bright daylight. We measured the ambient light that night. Starlight only, no moon, cloud cover blocking most stellar illumination. The light reaching ground level measured 0.03 lux. For context, we need roughly 50 lux to read comfortably. Office lighting typically provides 300 to 500 lux. This fox was hunting and running in light levels 600 times dimmer than what we consider barely adequate illumination. Yet it never stumbled, never hesitated. The thermal footage shows the fox weaving between trees, leaping over rocks, changing direction to follow scent trails, all while maintaining speeds that would challenge us even in full daylight. Its movement suggested it could see everything perfectly. But the light simply wasn't there to see with. The secret sits at the back of the fox's eye, a layer of tissue we share with cats and dogs and most nocturnal hunters, but one we've engineered to a remarkable degree of sophistication. It's called the tapetum lucidum, Latin for bright tapestry. And it's one of evolution's most elegant solutions to the problem of hunting in darkness. Here's what happens. Light enters the eye and passes through the lens. It hits the retina where photoreceptor cells called rods and cones convert photons into electrical signals our brain interprets as vision. In human eyes, any light that doesn't hit a photoreceptor on the first pass is absorbed by dark tissue behind the retina. Lost. Wasted. We get one chance to capture each photon, but the fox has something we lack. Behind its retina sits a reflective layer composed of 15 to 20 layers of specialized cells. These cells contain zinc-rich, crystalline structures arranged in parallel like tiny mirrors. When light passes through the retina without hitting a photoreceptor, instead of being absorbed, it reflects off this crystalline layer and passes back through the retina a second time. Every photon gets 2 chances to trigger a rod or cone cell. The fox essentially sees each photon twice. This doubles the amount of visual information the fox's brain receives from the same amount of available light. Where we see darkness, the fox sees a navigable landscape. Studies measuring this effect found the tapetum lucidum increases visual sensitivity by up to 50% in low light conditions. That's the difference between blindness and functional sight. And red foxes have taken this adaptation further than most canids. Researchers measured zinc concentrations in the tapetum lucidum across different species. Red foxes showed the highest zinc levels, exceeding even Arctic foxes and domestic dogs. Higher zinc concentration means more efficient light reflection, more light captured per photon, better night vision. You've seen this structure in action even if you didn't realize it. When you're driving at night and your headlights catch an animal on the roadside, its eyes glow back at you. That's eye shine. The tapetum lucidum reflecting your headlight beam straight back toward its source. In foxes, the glow typically appears green or blue-green, though the exact color varies based on the angle of observation and the specific mineral composition of the crystalline structures. But here's where our understanding hit an unexpected wall. Night vision explains how the fox sees in darkness. But watch footage of a fox diving headfirst into snow and you encounter a problem the tapetum lucidum doesn't solve. The impact should cause massive trauma. We're talking about an 8 to 12 pound animal accelerating to 10 to 13 feet per second, then driving its skull into a surface with enough force to penetrate 3 feet of packed snow. The deceleration forces should cause concussion, neck injury, broken facial bones, yet foxes do this dozens of times per night during winter hunting, night after night, season after season. And they don't just survive these impacts, they perform them with enough precision to grab a mouse in their jaws while still buried in snow. Something in the fox's anatomy is absorbing impact forces that would hospitalize us. The answer sits in the fox's skull. Researchers at Cornell University scanned fox skulls with high-resolution CT imaging. They compared red fox and Arctic fox skulls to those of other predators like lynx and puma. What they found was a specific skull shape that appears designed for exactly this type of high-speed snow penetration. The fox's snout is elongated and curves with a very specific geometry. When researchers ran computer simulations modeling snow penetration, that curvature did something unexpected. Instead of compressing snow, which creates resistance and violent deceleration, the fox's snout shape parts the snow. It slides through with minimal resistance. The snow flows around the skull rather than stopping it abruptly. Professor Seung-Hwan Jung from Cornell's Department of Biological and Environmental Engineering described it as the difference between a wedge and a needle. A wedge compresses material and creates massive resistance. A needle parts material and slides through. The fox's skull geometry is optimized to act as a needle, not a wedge. Impact forces drop dramatically. What should cause injury becomes survivable. But there's a secondary benefit we didn't anticipate. The elongated snout also allows the fox to reach deeper into snow. Those extra few inches of skull length mean the fox can grab prey that's slightly deeper below the surface. In computer models, this translates to a measurable increase in hunting success rate for mice located at greater depths. Evolution didn't just protect the fox from injury, it gave the fox access to prey other predators can't reach. And then there are the paws, 4 impact points that hit frozen ground or ice after every jump, each one absorbing forces that should shatter bones or tear ligaments. But examine a fox's paw and you find another piece of evolutionary engineering that took researchers decades to fully appreciate. The paw pads contain dense connective tissue with a very specific structure. Collagen fibers arranged in a three-dimensional matrix that compresses under impact, then rebounds instantly. It's not just padding, it's a shock absorption system that works like the suspension in your car, but at a microscopic level. The tissue deforms to absorb energy, preventing that energy from traveling up the leg into joints and bones. Tests measuring impact forces found that fox paws reduce peak force by roughly 30 to 40% compared to what the leg bones would experience without that specialized pad structure. That's the difference between chronic joint damage and a lifetime of high-impact hunting. But the paws solve another problem we didn't initially connect to hunting mechanics: traction on ice and frozen ground. The bottom of a fox's paw isn't smooth. It has a textured surface covered in tiny ridges and bumps. Under high magnification, these structures look almost like tire treads. They increase friction between paw and ground, preventing slipping during the critical moment when the fox launches into its hunting leap. You need stable footing for the magnetic hunting technique to work. If you slip even slightly during your approach, your alignment with the magnetic field shifts. Your calculated strike distance becomes inaccurate. You miss. The textured paw surface ensures that when the fox commits to a jump, it's jumping from exactly where it thinks it is. We're looking at 3 separate adaptations: enhanced night vision, impact-resistant skull geometry, and shock-absorbing paws that all evolved to support a single hunting strategy. Remove any one of these elements and the whole system fails. The fox needs to see in darkness to hunt at night. It needs the skull shape to survive snow penetration. It needs the paw structure to maintain alignment and absorb landing forces. But genetic changes take time, at least a few generations, and these explain only part of the story. Red foxes show adaptations that work in different seasons and different challenges. A fox thriving in summer faces completely different problems when winter comes. Food sources change, temperature drops, and the fox's own body must respond to seasonal changes that occur much faster than normal. Chapter 4. Night vision and shock-absorbing paws are engineering marvels, but they're permanent features. The fox's seasonal transformation is different. We see red foxes across the northern hemisphere in climates ranging from Mediterranean warmth to Arctic cold. The same species, the same basic body plan, yet somehow thriving in temperature ranges that span more than 100 degrees. That shouldn't work with fixed physiology. You optimize for cold or heat, not both. But the red fox found a solution that lets it function across that entire spectrum without migrating or hibernating. The solution lives in the fur. Twice a year, the fox sheds its entire coat and replaces it with something fundamentally different, not just thicker or thinner, structurally different fur designed for completely opposite challenges. And the transformation happens so gradually we barely notice until it's complete. Watch a red fox in late September. Its summer coat looks sleek and short. The red color appears vivid, almost bright, in good sunlight. The fur lies flat against the body with minimal bulk. Run your hand along that coat and you'd feel individual guard hairs over a thin layer of softer underfur. The whole coat measures maybe 1 inch thick at most. It's built for heat dissipation, for letting air circulate against skin, for preventing overheating during warm summer nights when the fox still needs to hunt. Now watch that same fox in late December. The transformation is remarkable. The coat has roughly doubled in thickness. The red color appears muted, almost brownish, because longer guard hairs now extend well beyond the underfur layer. And that underfur has become dense enough that you can barely see skin beneath it. The fox looks larger, fuller, like it gained 20% more body mass. But the fox didn't gain weight. It grew insulation. That winter coat contains two completely different fur types working together. The outer layer consists of long guard hairs that provide the red coloration we associate with red foxes. These hairs are relatively coarse and stiff. They shed water, they protect the underfur from snow and ice, and they trap a layer of still air close to the body. Still air is one of nature's best insulators. It prevents heat transfer far more effectively than solid materials at similar thickness. Beneath the guard hairs sits the underfur, soft, dense, and incredibly fine. Individual underfur fibers measure only a fraction of the diameter of guard hairs. They grow so densely packed that you'd find thousands of fibers per square inch of skin. This creates a thermal barrier that works like the insulation in your house walls. Heat generated by the fox's metabolism gets trapped close to the skin. Cold air outside can't penetrate through that dense mat of fiber to reach the body beneath. Studies measuring thermal conductivity of fox winter fur found it rivals some of the best insulating materials we've engineered. The coat maintains a temperature gradient of more than 40 degrees Fahrenheit from skin to outer fur surface in -20-degree weather. That means the fox's skin stays near normal body temperature even when the environment is cold enough to cause frostbite in exposed human skin within minutes. But here's the challenge we face when studying this. The transition between summer and winter coats doesn't happen quickly. It's not like the fox wakes up one morning and suddenly has different fur. The process takes weeks. Individual hairs fall out and are replaced one by one in a pattern that sweeps across the body. And during that transition period, the fox has to maintain thermal regulation with a partially incomplete coat. The shedding pattern follows a specific sequence. It starts at the head and shoulders, then moves backward toward the tail. This makes sense when you consider the fox's lifestyle. The head and front quarters experience the most physical wear from diving into snow and navigating through brush. Those areas need new fur first. The pattern also ensures the fox never has large bare patches that would create thermal weak points. Old fur remains in place until new fur beneath it is ready to take over insulation duties. We measured this transition timing across different latitudes. Foxes living in southern England begin their autumn molt in late September. Foxes in northern Scandinavia start in early August. The farther north you go, the earlier the transition begins. That suggests day length triggers the molt rather than temperature. The fox's body responds to shortening days as a signal that winter is approaching. It starts growing winter fur while weather is still warm, ensuring full insulation is ready before the first hard freeze. The spring transition works in reverse but follows similar patterns. As days lengthen, foxes begin shedding heavy winter fur and replacing it with lighter summer coat. This transition takes even longer than the autumn molt, sometimes stretching across 3 full months. You'll see foxes in April that look ragged and patchy as clumps of winter underfur fall out in irregular patterns. By July, the transformation completes and the sleek summer coat is back. But seasonal coat change isn't just about temperature regulation, it's also about camouflage. That bright red summer coat works well against summer vegetation. Green leaves, brown soil, golden grasses. The fox's coloration blends surprisingly well despite seeming vivid to our eyes. But winter changes everything. Snow covers the landscape. Brown and red stand out against white. The fox becomes visible from distances that would be impossible during summer. Yet the winter coat doesn't turn white. Arctic foxes do that. Their winter coats become almost pure white for camouflage against snow. Red foxes keep their reddish-brown coloration year-round. So how do they avoid being spotted against snow by prey and predators? The answer involves something we call disruptive coloration. The winter coat isn't uniform red. It contains white, black, and grey patches that break up the fox's outline. White throat and chest, black legs, grey highlights along the flanks. These patches prevent the eye from recognizing the fox's body shape against complex backgrounds. Snow rarely creates pure white landscapes. There are shadows, exposed earth, dead vegetation, rocks. The fox's mixed coloration lets it blend into that visual complexity in ways solid coloring never could. We tested this by analyzing predation rates on foxes during winter versus summer. If the winter coat made foxes more visible, we'd expect higher predation from wolves, coyotes, and large raptors. But the data shows no seasonal difference in predation rates. The winter coat provides adequate camouflage despite not matching the snow. There's another element to seasonal coat change we're only beginning to understand: scent. Fur carries chemical signals that communicate information to other foxes: breeding condition, territory ownership, individual identity. When the fox sheds and replaces its entire coat twice per year, it's also shedding the chemical history embedded in that fur. The fresh coat provides a clean slate for new scent marking that reflects current status rather than outdated information from months past. This matters during breeding season. Female foxes come into estrus once per year, typically between December and February depending on latitude. The spring molt that follows breeding season erases chemical traces of mating activity. By the time summer arrives, you can't tell from scent alone whether a female bred successfully or remained unmated. That information privacy might reduce harassment from males and help females raise their young without constant interference. But the coat change creates vulnerabilities we don't often consider. During those transition periods when old fur is falling out and new fur is growing in, the fox's insulation is compromised. A sudden cold snap during autumn molt or an unexpected heat wave during spring molt can cause real problems. The fox's thermal regulation system is temporarily less effective exactly when weather becomes unpredictable. Climate change is making these transition periods increasingly risky. Warmer autumns delay the need for winter coats, but sudden temperature drops still occur. Foxes caught mid-molt during an early freeze face genuine danger. Their partially grown winter coat provides inadequate insulation for the actual temperature, and there's no way to accelerate the molt. Hair grows at a fixed rate, determined by biology, not by current need. We've documented fox mortality events during these vulnerable periods, not common, but present in the data. Foxes found dead with no obvious cause of injury or disease, but with coats showing incomplete seasonal transition. The leading hypothesis points to hypothermia during unexpected cold snaps that overwhelmed inadequate insulation. The coat also serves functions beyond temperature and camouflage. It protects skin from physical damage. Thorns, sharp grasses, and rough surfaces that would tear skin are deflected by dense fur. It provides cushioning during those high-impact snow dives we discussed earlier, and it helps shed water, keeping the insulating underfur layer dry even when the fox is moving through wet snow or rain. But maintaining that coat requires energy. Growing new fur demands protein. A fox replacing its entire coat needs roughly 20% more food during molt periods to supply the amino acids required for hair synthesis. Urban foxes with reliable food access handle this easily. Rural foxes in marginal habitats sometimes struggle. We see thinner, lower quality coats in foxes that were nutritionally stressed during molt periods. The quality of the coat reveals the fox's recent history. Thick, lustrous fur indicates good nutrition and health. Thin, patchy, or dull fur suggests stress, disease, or inadequate food access. Wildlife biologists can assess fox population health just by examining coat condition. It's a visible record of how well the individual is coping with its environment, and that record changes with every season, wiping away the past and showing us only the present. The fox you see today might look healthy and well-fed, but 6 months ago that same fox might have been struggling. The new coat hides that history. It gives the fox a fresh start twice per year, allowing recovery from temporary hardship without permanent visible consequences. This seasonal transformation reminds us that adaptation isn't always about permanent change. Sometimes survival means flexibility, the ability to shift between different modes as conditions demand. The fox doesn't commit to winter or summer. It commits to both, transforming itself season after season in an endless cycle that's been running for thousands of years. But the coat is silent. It doesn't announce when it's changing or why. For communication across distances, for coordinating with other foxes without meeting face to face, the red fox needed something completely different, something that carries through darkness and across miles of territory without requiring direct contact. Chapter 5. The forest settles into night. Temperature drops, shadows lengthen between trees, and somewhere in the darkness a sound cuts through the silence. Not quite a scream, not quite a bark. Something between the two that makes you stop walking and wonder what animal could produce such a noise. That's a fox talking, and what it's saying depends on who's listening. We spend our lives communicating through words, thousands of them, each carrying specific meaning that we learned through years of practice. But before humans developed language, before we had words for things we wanted to express, we made sounds, grunts and calls and cries that conveyed emotion and intent without needing complex grammar. The fox never left that simpler system behind. It still speaks in pure sound, no words, no sentences, just vocalizations that carry meaning through tone and rhythm and context. Scientists observing wild foxes over multiple years identified more than 20 distinct vocalizations in the red fox repertoire. 20 different sounds, each one serving a different purpose. Some loud enough to hear from half a mile away, others so quiet you'd miss them standing 10 feet from the fox. Together they form a communication system complex enough to coordinate social behavior across territories spanning several square miles. The most famous fox sound is the scream. You've probably heard it described as sounding like a woman in distress. That description is accurate enough to be disturbing. Play a recording of a vixen screaming during mating season, and people will tell you it sounds human, not animal. The pitch, the rhythm, the emotional quality, all of it reads as human vocal distress to our pattern-recognizing brains. But the fox isn't in distress, it's advertising. Female foxes produce these screams primarily during winter breeding season, roughly December through February depending on latitude. the sound carries across remarkable distances. On cold, still nights when sound travels well, a vixen's scream can reach listeners more than a mile away. That's the point. She's announcing her presence and her reproductive status to any male foxes within earshot. Male foxes respond with their own screams, slightly different in pitch and structure. Where the female's scream sounds like a single drawn-out cry, the male version often comes in shorter bursts, a series of sharp vocalizations rather than one continuous call. Males use these screams to warn competing males away from females. Territory enforcement through sound. The message is clear without needing translation. She's spoken for, go find your own. But screaming isn't the only sound foxes make during breeding season. There's also geckering. That's the technical term, though it barely describes what the sound actually is. Imagine a stuttering chatter mixed with brief yelps and something like a cough. It's a guttural, rhythmic sound that foxes produce during aggressive encounters. Two males competing for breeding access, a territorial dispute between neighbors, juveniles play fighting outside the den. All of these situations trigger geckering. The sound serves as both threat and assessment. The fox producing the loudest, longest geckering sequence usually wins the encounter without physical combat. It's a vocal display of fitness and aggression that often resolves conflicts before they escalate to biting and injury. Energy-efficient conflict resolution through sound alone. Then there are the barks, quick, sharp, high-pitched vocalizations that don't sound much different from a small dog barking. Foxes use barks for multiple purposes depending on context. A single bark might be an alarm call. Something unexpected appeared, potential danger detected. The fox alerts others in the area without specifying what the threat is, just a general warning to be cautious. Multiple barks in rapid sequence serve different functions. Parents bark at their cubs to signal feeding time or to call them back to the den. Cubs bark back in response, a back-and-forth exchange that helps parents locate offspring in tall grass or dense brush. The barks also encode individual identity. Research analyzing fox bark patterns found that foxes can identify which individual is barking based on subtle variations in pitch and rhythm. Your bark is as unique as your voice. There's also a sound called the wow 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 contact call. It sounds exactly like it's named. 3 short, bird-like notes repeated in quick succession. Foxes use this call to maintain contact with family members or neighbors when visual contact is impossible. You're hunting in dense vegetation. Your mate is somewhere nearby, but out of sight. You produce the wow 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 call. If everything is fine, your mate calls back. If there's no response, you know something changed, and investigation might be warranted. What's remarkable about this particular call is how unfox-like it sounds. Play it for someone without context and most people guess it's a bird, not a mammal, certainly not a predator. That might be intentional. A contact call that doesn't sound like a fox is less likely to alert prey species to your presence. Cryptic communication that flies under the awareness of animals listening for predator sounds. Cubs produce their own specialized vocalizations that adults don't replicate. There's a sound called warbling, a sort of rising and falling whine that very young cubs make when they're alone and seeking attention. The warble triggers parental response. A mother hears that sound and returns to the den to check on her offspring. As cubs mature, the warble disappears from their vocal repertoire, replaced by adult vocalizations. There's also something researchers call a whelping call. Newborn cubs make this sound during their first weeks of life. It's higher pitched and more rhythmic than the warble, a steady cry that communicates basic needs: hungry, cold, uncomfortable. The mother responds by nursing, warming, or adjusting the cub's position in the den. Simple communication for simple needs. But not all fox communication is loud or carries across distance. Some of the most important sounds foxes make are quiet. Intimate vocalizations used between individuals in close proximity. A mother makes soft huffing noises while grooming her cubs. Brief coughs that seem to have calming effects. Cubs relax when they hear these sounds, becoming still and quiet while the mother works. There are also submissive whines. Lower-ranking foxes produce these when approaching dominant individuals. The whine can escalate into a shriek if the dominant fox displays aggression. It's a vocal acknowledgement of hierarchy, a way of saying, "I'm not challenging you," before physical interaction occurs. This prevents unnecessary fights that would waste energy and risk injury for both participants. The volume, pitch, and duration of these sounds all carry information. A short bark means something different than a long bark. A high-pitched whine conveys different intent than a low-pitched whine. Context matters too. A bark produced while running away from something communicates differently than a bark produced while approaching something. Foxes reading these acoustic signals understand nuances we're only beginning to decode, and here's where the communication system reveals its true sophistication. Foxes vocalize throughout the year, but they're most vocal during winter. Breeding season drives increased communication, but even outside those critical months, foxes maintain acoustic contact with neighbors and family members. That means these sounds aren't just about mating, they're about maintaining social structure across territories where foxes might not see each other for days at a time. Your territory borders another fox's territory. You rarely encounter each other directly, but both of you need to know the boundary is being respected. Periodic vocalizations establish presence without requiring face-to-face meetings. You call from your side, your neighbor calls from their side. The acoustic boundary gets reinforced without anyone needing to leave their hunting grounds. Urban foxes added another layer to this communication system. City noise masks many natural sounds, traffic, construction, human voices. All of it creates acoustic interference that makes quiet vocalizations harder to detect. Urban foxes responded by shifting their vocal behavior. They vocalize more at night when city noise drops, and they've increased the volume of some calls to overcome ambient noise pollution. Studies recording urban versus rural fox vocalizations found that city foxes produce barks and screams at measurably higher volumes than wilderness foxes. The difference averages around 10 to 15% louder. Not dramatic, but enough to compensate for background noise that would otherwise drown out their calls. But the most intriguing aspect of fox vocal communication isn't the sounds themselves, it's how infrequently foxes actually use them. In more than 400 hours of tracking foxes through Bristol, researchers recorded only 77 vocalizations, each lasting just a few seconds. That means foxes spent more than 99% of their tracked time completely silent. They communicate only when necessary. The rest of the time they move through their territories without announcing their presence. And this makes evolutionary sense. Vocalizations attract attention, not just from other foxes, but from predators, prey, and competitors. Every sound you make is a risk. It might alert the rabbit you're stalking, might draw the attention of wolves or coyotes, might bring a larger predator investigating your territory. So foxes remain quiet unless the benefit of communication outweighs the risk of being heard. And when they do vocalize, the sounds travel through darkness and across distances, carrying messages between foxes that may never meet, a conversation without words, territory negotiated through screams and barks echoing across midnight forests, families coordinated through calls that pierce the night and fade into silence before prey animals can locate their source. But sound alone can't sustain a fox through winter. When snow covers the landscape and temperatures drop below freezing, the fox needs more than vocal communication to survive. It needs food, and not just enough for today, enough for tomorrow and the day after and the weeks ahead when hunting might become impossible. Chapter 6. Winter arrives slowly, then all at once. The first frost appears on grass one October morning. Leaves turn brown and fall. The temperature drops week by week until the landscape transforms into something unrecognizable. And prey disappears. Not gone entirely, but hidden. Mice stay in their tunnels beneath the snow. Rabbits shelter in dense brush. Birds migrate south or hunker down in protected roosts. The abundance of summer vanishes, replaced by scarcity that tests every predator's ability to survive. The fox anticipated this months ago. Back in July, when prey was everywhere and hunting was easy, the fox started preparing. Not consciously planning for winter like we might stock a pantry before a storm, but following instincts refined over millennia. Instincts that tell the fox to do something that seems wasteful in the moment but becomes essential later. Bury the food you don't need today. You'll need it when tomorrow brings nothing. Researchers following radio-collared foxes through summer and autumn documented this caching behavior in remarkable detail. A fox catches a mouse, more food than it can eat immediately. Instead of consuming the entire mouse or abandoning the excess, the fox carries it 20 or 30 yards from the capture site. It digs a small hole with its front paws, places the mouse inside, covers it with soil and leaves, presses the surface down with its nose, then walks away. The entire process takes less than a minute. The cache looks like undisturbed ground once the fox finishes. No obvious markers, no visual cues that food sits buried there. Just another patch of forest floor that looks identical to every other patch nearby. Yet the fox will return to that exact spot weeks or even months later, dig up the mouse and eat it. How? How does the fox remember the location of one mouse among potentially hundreds of caches scattered across a territory that might span 3 square miles? We cache things too. We put groceries in cupboards and remember where we place them because the cupboard is a permanent landmark. But the fox is caching in a landscape where everything moves and changes. Leaves blow away, snow covers the ground, seasonal growth transforms the vegetation. The visual environment the fox sees in November bears little resemblance to what it saw in July when it buried that mouse. Yet somehow the fox finds its caches with accuracy that suggests something more sophisticated than random searching. Studies tracking cache recovery rates found that foxes successfully retrieve 60 to 70% of the food they bury. That's far too high to be explained by chance. If the fox was just digging randomly in areas where it remembered caching food, success rates would be much lower. The fox is using spatial memory with precision we're only beginning to understand. We think the fox creates a mental map of its territory. Not a visual map like we might draw on paper, but a spatial representation that encodes locations relative to permanent landmarks. That cache is 15 feet northeast of the large oak tree. Another cache is 30 feet south of the boulder near the stream. A third sits 12 feet west of where two deer trails intersect. The fox isn't memorizing what the location looks like. It's memorizing geometric relationships between the cache and surrounding features that don't move. This type of memory is called spatial cognition. Many animals possess it to varying degrees. Squirrels use it to relocate acorns they buried months earlier. Clark's nutcrackers, a bird species, cache tens of thousands of pine seeds across mountain landscapes and recover them throughout winter. But what makes the fox's version particularly impressive is the scale. We're not talking about dozens of cache sites. We're talking about hundreds, potentially thousands over the course of a year. One study tracking a single fox throughout autumn documented 437 separate caching events, 437 different locations where this fox buried food items ranging from mice to bird eggs to insects. The researchers marked each cache location with GPS coordinates. Then they monitored how many the fox retrieved as winter progressed. By late February, the fox had recovered 281 caches, 65% success rate across nearly 300 separate locations spanning almost 4 square miles. That's a level of spatial memory comparable to what we see in animals specifically adapted for caching. Animals whose entire survival strategy revolves around food storage. Yet the fox does this alongside all its other behaviors: hunting, territorial maintenance, social interactions, breeding. The caching is just one component of a broader lifestyle, not the defining feature, which makes the cognitive achievement even more remarkable. But the fox doesn't cache randomly throughout its territory. There are patterns to where and when caching occurs. Prime caching habitat includes areas with soft soil for easy digging, near permanent landmarks for spatial reference, in locations with good drainage so caches don't flood during rain, and preferably in spots the fox visits regularly during its normal territorial patrols, making cache recovery a natural part of its routine rather than a special trip. The timing of caching follows food availability. Peak caching occurs during late summer and early autumn, when prey populations reach their annual maximum. Young mice and voles born in spring have matured into adults. Multiple generations overlap. Prey density in good habitat can reach remarkable levels during this period. The fox finds itself catching more food than it needs, sometimes multiple prey items during a single hunting session. That surplus gets cached, but not all prey items get cached equally. The fox makes choices about what's worth burying and what should be consumed immediately. Small prey like insects or earthworms get eaten on the spot. The energy cost of caching them exceeds their nutritional value. Medium-sized prey like mice and voles are ideal catching candidates, large enough to provide meaningful calories when recovered later, small enough to bury quickly without excessive effort. Larger prey like rabbits present a different challenge. Too big to cache whole, so the fox might consume part immediately and cache the remainder if possible. Cached food doesn't last forever underground. Decomposition occurs even in buried items. Bacteria and fungi break down tissues. By spring, caches buried in autumn have degraded significantly. Some become inedible. But winter cold slows decomposition dramatically. A mouse buried in October remains relatively fresh when recovered in January because cold temperatures preserve tissue almost like refrigeration. The fox isn't preserving food through any special treatment, it's relying on winter itself to act as a natural freezer. There's also theft to consider. Other foxes might discover and raid caches, so might other species. Raccoons, skunks, and ravens all consume cached food if they find it. This creates evolutionary pressure for the fox to cache in inconspicuous locations and to spread caches widely across its territory. If you concentrate all your stored food in one area, a single discovery by a competitor could wipe out your entire reserve. But if you distribute hundreds of caches across miles of territory, losing a few to theft doesn't threaten overall winter survival. We've watched foxes recache items they've recovered, dig up a mouse from one location, carry it to a new location, and bury it again. This happens when the fox isn't hungry at the moment of recovery, or when it finds a better caching location nearby. The food gets moved to improved storage rather than wasted. It's a flexibility in the caching system we didn't expect to see. But what happens when the fox can't find a cache? When spatial memory fails, or when theft has emptied a spot the fox remembers? The fox shows no obvious frustration. It simply moves to the next location in its mental map and tries there. Cache recovery isn't an all-or-nothing proposition, it's a probability game. Most of the time you find food where you buried it. Sometimes you don't, but as long as your success rate stays above 50%, you've gained more energy than you invested in the caching behavior. And here's something we find particularly interesting about the system. Young foxes don't cache effectively during their first year. They bury food in random locations without clear spatial patterns. Recovery rates for juvenile caches hover around 20 to 30%. Much lower than adults. This suggests caching isn't purely instinctive. It requires learning and practice. Young foxes have the instinct to bury surplus food, but they need experience to develop the spatial memory systems that make recovery efficient. We see them learning by watching their parents. A vixen caches food near the den while cubs observe. Later, those cubs attempt their own caching, mimicking the behaviors they witnessed. Early attempts are clumsy. Poor location choices, shallow burial, inadequate concealment. But with repetition, success rates improve. By their second year, young foxes cache and recover at near-adult efficiency. Urban foxes show interesting variations in caching behavior. Cities provide more consistent food availability throughout winter. Garbage bins don't hibernate. Human food waste continues year-round. This reduces the survival pressure that drives caching in rural foxes. Some urban fox populations show decreased caching frequency compared to rural populations. They still cache, but less extensively because the behavior is less critical for winter survival. Yet, even urban foxes maintain the caching instinct. Researchers observing London foxes documented caching of human food items. Pizza crusts buried in garden flower beds, chicken bones cached beneath bushes. The fox's instinct to store surplus remains active even when the food source is fundamentally different from natural prey. The caching system represents forward thinking without conscious thought. The fox in July has no concept of January's hardship. It doesn't think about future hunger. But evolution programmed the instinct to cache because foxes that cached survived winters, that killed foxes that didn't. Over thousands of generations, that selection pressure built a behavior pattern so deeply ingrained it activates automatically whenever surplus food appears. And so the fox continues burying its future meals, one mouse at a time, one cache site among hundreds, building a distributed food reserve that exists only in memory, invisible to others, waiting beneath soil and snow for the day when fresh hunting fails and survival depends on finding what you hid when times were good. The system works. It's worked for as long as foxes have existed, and it will keep working as long as the fox remembers where it buried the things it needs when winter refuses to provide. Chapter 7. The same species, the same evolutionary history. Yet a fox in rural Scotland and a fox in downtown London live such different lives that watching them feels like observing two separate animals. Not in appearance, they look identical, red coat, white tipped tail, sharp features, but in behavior, in daily routine, in how they interact with their world, the differences run deep. Morning arrives in the Scottish Highlands. The rural fox returns to its den after a night of hunting across open moorland. It's travelled perhaps 4 or 5 miles since sunset, following prey trails through heather and gorse. The hunting was difficult. 3 attempts before catching a single vole. Another hour before finding a second. Energy expended versus energy gained barely breaks even some nights. But this is normal. This is how it's always been. The fox settles into its den beneath a rocky outcrop. The space is cold but dry, insulated by earth and stone. Silent except for wind moving through the heather outside. The fox sleeps alone. Its mate occupies a separate den half a mile away. They'll meet again tonight when territories overlap during hunting hours, but days are spent in solitude. Meanwhile, in London, another fox makes its way back through residential streets. Dawn is breaking. Early commuters begin their drives to work. The fox moves along garden fences, staying low, keeping to shadows even as daylight grows. It spent the night within a 6-block radius, less than half a mile of total distance travelled. Yet it found more food than the rural fox will encounter all week. 2 garbage bins tipped over, leftover kebab, half a sandwich, some chicken bones that required careful eating but provided good nutrition. A compost pile that revealed earthworms and beetle larvae. A garden where mice had nested beneath the shed. The urban fox caught 3 mice with less effort than the rural fox expended catching 1 vole. Now the London fox returns to its den beneath a garden shed. The space is warmer than the Highland den. Heat escapes from the house above, raising the temperature inside the crawl space by several degrees. The difference matters during winter. It means less energy spent maintaining body heat, more energy available for other needs. But the urban fox doesn't sleep alone. Another adult fox shares the den space. They're not mates, not related, just 2 foxes that tolerate each other's presence because good denning sites in cities are valuable enough to share. This social flexibility doesn't exist in rural populations. Wild foxes maintain strict territorial boundaries. Sharing prime den space with a non-family member would trigger aggression. But urban foxes develop different rules for different circumstances. The dietary differences between city and country foxes reveal themselves in unexpected ways. Rural foxes consume roughly 80% natural prey. Rodents, rabbits, birds, insects, food that requires active hunting. The remaining 20% comes from scavenged items. Carrion, food other predators left behind. The diet varies seasonally but stays within these general proportions. Urban foxes flip this ratio. Natural prey still matters. They still hunt mice and birds when opportunities arise. But human food sources provide 40 to 50% of their total calories. Not because urban foxes prefer human food, but because it's consistently available with minimal effort. Why spend an hour stalking a mouse when you can find equivalent calories in a trash bin within 10 minutes? This dietary shift changes the fox's daily activity patterns. Rural foxes must hunt actively most of the night to meet caloric needs. They're constantly moving, searching, stalking. Rest periods are brief. Hunting is work. Urban foxes spend less time foraging. They visit known food sources on a circuit. Check this garbage bin. Investigate that compost pile. Hunt in the garden where mice are common. The route becomes predictable, efficient, less distance for more food. We see this reflected in territory size. Rural fox territories average 1 to 2 square miles in good habitat, larger in poor habitat where prey is scarce. The fox needs enough space to support its food requirements. Too small a territory means starvation. Urban territories shrink dramatically. Some London foxes maintain territories of only 15 to 20 acres, less than a tenth the size of rural territories. High food density allows smaller ranges, but smaller territories mean more neighbours. In the Highlands, a fox might not encounter another fox for days. Territories border each other, but the actual foxes occupying those territories rarely meet. They communicate through scent marks and occasional vocalizations. Direct interaction is uncommon. Urban foxes encounter each other constantly. 20 to 24 foxes per square mile means your neighbors are always close, always visible, always present. This forced proximity changed how urban foxes handle social interactions. Rural foxes react aggressively to territorial intruders, chase them out, fight if necessary, maintain strict boundaries. Urban foxes developed more tolerance. They still defend core areas around dens, but territory boundaries became fuzzy. Overlap zones where multiple foxes hunt without constant conflict. A sort of informal agreement to share resources rather than fight over every garbage bin. Young foxes show the clearest behavioral differences between urban and rural populations. In wilderness, juvenile foxes disperse from their birth territory around 7 to 8 months old. They travel until finding vacant territory to claim as their own. Dispersal distances average 10 to 15 miles, sometimes farther. The journey is dangerous. Young foxes crossing unfamiliar territory face predation, starvation, and conflicts with established residents. Urban juveniles often don't disperse at all. They stay in their birth territory into adulthood. Sometimes they remain there permanently, sharing space with parents and siblings in multi-fox groups. This shouldn't work. Competition for food should force dispersal, but urban food abundance supports higher densities. The territory can feed multiple adults where a rural territory barely feeds one. Disease pressure differs between populations. Rural foxes face parasites and pathogens common in wildlife. Mange mites, intestinal worms, tick-borne diseases. But low population density limits disease transmission. Sick foxes often die alone in their dens without infecting others. Urban foxes live closer together. Disease spreads more easily through dense populations. Mange outbreaks can devastate urban fox communities, killing 40 to 60% of infected populations before burning out. Yet urban foxes also develop different disease resistance patterns. Exposure to human pathogens and urban pollutants may select for immune system variations. We're seeing preliminary genetic evidence of this in some cities. Genes related to immune function showing signatures of selection in urban populations. Evolution responding to novel disease pressures within just a few dozen generations. Early morning in the desert. The fox emerges from its den as the sky begins to lighten. The night was cold. Desert temperatures swing dramatically between day and night. This temperature cycling creates something the fox can exploit: dew. As air cools overnight, moisture condenses on surfaces, rocks, plants, even sand grains in the right conditions. The amount is tiny, maybe a few drops per square foot. But the fox knows where dew accumulates most heavily. Shaded rock faces, north-facing slopes, areas where cold air pools during night hours. The fox licks moisture from rocks, methodical movements covering every damp surface within its territory. It takes time. An hour of work might yield an ounce of water, but an ounce is survival. The fox moves from rock to rock, plant to plant, harvesting condensation before sunrise, evaporates it back into atmosphere. This behavior exists in places we don't associate with water scarcity too. Rural foxes in temperate regions lick dew from grass on summer mornings. Not because water is unavailable elsewhere, but because dew is convenient. Why travel to a stream when moisture exists right here, coating every blade of grass in your hunting grounds? But dew alone isn't enough in true desert. The fox needs supplemental sources, and it finds them in surprising places. Prey provides water. A mouse is roughly 70% water by weight. Eat 3 mice and you've consumed not just calories, but significant moisture. Insects offer hydration too. Beetles, grasshoppers. Their bodies contain enough liquid that a fox eating primarily arthropods during summer months can meet much of its water requirement through food alone. Plants contribute as well. Desert foxes eat more vegetation than their temperate relatives, not for calories primarily, for moisture, fruits and berries when available, succulent plants that store water in their tissues, roots dug from underground where moisture remains even after surface soil dries completely. We tracked water intake in captive foxes fed diets mimicking wild prey availability. Foxes eating fresh prey consumed 60% less free water than foxes eating dry food. The moisture content of natural prey reduced their drinking needs dramatically. In the wild, this means a fox with good hunting success can survive longer between visits to actual water sources. But eventually, most foxes need to drink. And finding water in arid landscapes requires knowledge passed down through generations. The location of reliable water sources becomes critical survival information. Desert fox mothers lead their cubs to every spring and seep within their territory during the cubs' first summer. The young foxes learn a mental map of where water exists, which sources run year-round, which dry up by August, which require digging to access. Some water sources aren't obvious. Bedrock catchments that collect and hold rainwater for weeks after storms. Seeps where groundwater reaches the surface through cracks in stone. Dry stream beds where digging down 2 feet reveals damp sand and eventually flowing water beneath. The fox learns to read subtle cues that indicate these hidden sources. Vegetation provides clues. Certain plant species only grow where groundwater sits close to surface. A lone cottonwood tree in otherwise barren landscape signals water beneath. The fox doesn't understand why the tree grows there. It just knows that where the tree stands, digging produces water. Human activity created new water sources that desert foxes exploit extensively. Cattle troughs, irrigation systems, swimming pools, ornamental ponds, golf courses with artificial lakes. These permanent water sources allowed fox populations to expand into desert regions they couldn't have occupied historically. We accidentally became water providers for animals we never intended to support. But urban water sources bring complications: chlorinated swimming pools, antifreeze leaking from vehicles, pesticides in irrigation runoff. Not all human water is safe to drink. We've documented cases of fox poisoning from contaminated urban water sources. The fox's ability to exploit human infrastructure comes with risks its evolutionary history didn't prepare it for. Metabolic adaptations help too. Foxes produce concentrated urine when water is scarce. Kidneys extract more water from waste, returning it to the bloodstream. The urine that results is darker, more concentrated, excreting waste products in minimal fluid volume. This physiological adjustment happens automatically as hydration status changes. Well-hydrated foxes produce dilute urine. Dehydrated foxes concentrate it, conserving every possible drop. Behavior changes under drought stress. The fox becomes less active during daylight, stays in its den where temperatures remain 20 to 30 degrees cooler than surface. Reduces energy expenditure and therefore water loss through respiration and heat dissipation. Hunting shifts to night when cooler air reduces the physiological cost of movement. Panting is expensive from a water perspective. It cools the body through evaporation, effective for temperature regulation but costly when water is limited. Desert foxes pant less than you'd expect. They tolerate slightly higher body temperatures during hot periods rather than waste water cooling themselves. This thermal tolerance has limits. Core temperature can't rise too high without causing damage, but a fox can operate at body temperatures we'd find uncomfortable. Buying itself time before panting becomes necessary. The tail serves unexpected functions in water conservation. That bushy, distinctive tail isn't just for balance and communication. Foxes sleeping during hot days drape their tails across their faces. The fur creates shade, reduces direct sun exposure on delicate facial tissues, and the tail's surface area helps dissipate heat without requiring water loss through panting. A multifunctional structure with benefits we're still cataloguing. Some fox populations develop behaviors specific to their environments. Foxes living near coastlines learn to exploit tidal zones. At low tide, pools trapped between rocks contain trapped seawater and marine life. The fox won't drink salt water. That would worsen dehydration, but it will eat marine invertebrates, extracting moisture from their tissues while letting their salt content pass through its digestive system. Arctic foxes face the opposite challenge. Water exists everywhere as ice and snow, but consuming frozen water costs energy. The body must melt the ice using metabolic heat. In extreme cold, eating snow can actually increase dehydration by consuming more energy than the melted water provides. Arctic foxes prefer to drink from the few streams that remain liquid through winter. When that's not possible, they eat snow, but only in small amounts, balancing water gain against energy cost. Red foxes in temperate regions rarely think about water. Streams run year-round. Rain replenishes surface water. Prey contains adequate moisture. The fox drinks when convenient, but never faces true water stress. It's easy to forget that water acquisition is a non-issue for most fox populations. Only in extreme environments does this basic need become a daily challenge, requiring specialized knowledge and behavior. But even temperate foxes remember the skills. A drought year dries up normal water sources. The fox shifts to behaviors it doesn't usually need, seeking dew, eating more moisture-rich prey, traveling farther to reliable water sources. The flexibility remains even when circumstances don't demand it, ready to activate when conditions change. Climate patterns shift. Droughts become more frequent in some regions. Traditional water sources fail, and the fox adapts again, learning new routes to new sources, changing behavior to match changing reality. The same flexibility that let foxes colonize cities lets them survive in landscapes where water becomes increasingly scarce. The desert fox walks back to its den as dawn breaks. Another night passed, another day beginning. Water secured from dew and prey will sustain it until evening when the cycle repeats. This pattern has worked for generations. Will continue working as long as the fox remembers where to look, where to dig, when to drink, and as temperatures rise globally, as precipitation patterns shift and deserts expand into what were once temperate zones. The strategies desert foxes perfected become relevant to populations that never needed them before. Knowledge spreading, behaviors adapting. The fox finding water where water grows scarce. The animal that learned to hunt with magnetic fields, to see in darkness, to thrive in cities, now faces perhaps its greatest test, surviving a planet that's changing faster than ever before, and somehow the fox keeps finding answers. Chapter 10. The world changes, it always has. Ice ages come and go. Forests become grasslands, rivers shift course, species adapt or disappear. But the pace of change matters. Evolution works on timescales measured in thousands of years. When environments transform over millennia, populations have time to adjust. Genetic variations that provide advantages spread gradually through breeding populations. Behaviors shift incrementally as each generation faces slightly different conditions than the one before. But change is accelerating now, average temperatures rising, precipitation patterns shifting within decades rather than centuries, habitats fragmenting as human development expands. The fox that survived ice ages and continental drift now faces transformations happening within single lifetimes, too fast for genetic evolution. Fast enough that the fox must rely entirely on behavioral flexibility to keep pace. And so far, it's working. The red fox remains one of the most widespread carnivores on Earth. Its range extends across the entire northern hemisphere, from Arctic tundra to Mediterranean coasts, from remote wilderness to dense cities. No other land predator occupies such diverse habitats successfully. That success story continues even as conditions change in ways that stress many other species toward decline. Part of the fox's resilience comes from diet. Specialists suffer when their food source declines. Pandas depend on bamboo. If bamboo forests shrink, pandas have nowhere else to turn. But the fox eats nearly everything: rodents, birds, insects, fruits, carrion, human garbage. This dietary flexibility means environmental changes that eliminate one food source, leave others available. The fox shifts its menu and continues surviving. Temperature tolerance helps too. Red foxes function in environments ranging from -40 degrees to +90 degrees Fahrenheit. Arctic populations have thicker winter coats and different behaviors than Mediterranean populations, but they're the same species, the same genetic template, expressing differently based on local conditions. As temperatures rise in northern regions, foxes already living there possess the physiological range to handle several degrees of warming without requiring evolutionary changes. But tolerance has limits. Arctic foxes, a separate species adapted specifically for extreme cold, are struggling as their habitat warms. They're being displaced by red foxes moving northward into territories that were previously too cold. The red fox's flexibility becomes a competitive advantage. It can exploit the warming Arctic in ways specialized Arctic foxes cannot match. We're watching one species expand while another contracts, driven by temperature changes of just a few degrees. Habitat fragmentation presents different challenges, forests broken into isolated patches by roads and development. Fox populations that once connected across continuous territory now live in islands separated by barriers they rarely cross. This isolation reduces genetic diversity. Small populations cut off from others accumulate mutations and lose the genetic variation that helps species adapt to new conditions. Yet foxes handle fragmentation better than many species. They cross roads, though not without risk. Vehicle strikes kill thousands annually, but enough foxes make successful crossings that gene flow between populations continues. Wildlife corridors help, underpasses designed for animal movement, green spaces connecting fragmented habitats. These structures give foxes and other species pathways through landscapes otherwise hostile to wildlife movement. Urban expansion creates winners and losers in wildlife communities. Many species decline as cities grow, but the fox does something remarkable. It colonizes the city itself, turns the heart of human development into functional habitat. This ability to live alongside us, to exploit our waste and our structures, gives the fox refuge in places other predators cannot occupy. Some conservationists worry this urban adaptation might weaken wild populations. If cities support higher fox densities than wilderness, urban foxes might eventually outnumber rural ones. Genetic differences between populations could increase, urban and rural foxes diverging into distinct ecotypes with different behaviors and physiological traits. We're already seeing preliminary evidence of this in cities where fox populations have existed for multiple generations. But divergence isn't necessarily negative, it's adaptation. Urban foxes developing traits suited to city life while rural foxes maintain traits suited to wilderness creates resilience at the species level. If one habitat type becomes unavailable, populations in the other persist. Diversity of populations across diverse environments strengthens the species as a whole. Disease remains a wild card. Mange outbreaks devastate fox populations periodically. Rabies, in regions where it occurs, can reduce fox numbers substantially, but populations recover. Within a few years of a major disease event, fox numbers typically return to pre-outbreak levels. High reproductive rates allow rapid recovery. A single vixen can produce 4 to 6 cubs annually. Even with high juvenile mortality, enough survive to replace losses and rebuild populations. Climate change affects prey availability. Rodent populations shift in response to changing temperatures and rainfall patterns. Birds alter migration timing. Insect emergence happens earlier or later than historical norms. These shifts in prey ecology cascade up to affect predators. But the fox's dietary breadth buffers it against these changes. One prey species declines while another increases. The fox shifts hunting focus and adapts. Human attitudes toward foxes vary regionally. In Britain, foxes receive general tolerance despite occasional conflicts. Most people accept their presence as part of the urban ecosystem. In some rural areas, foxes face active persecution as perceived threats to poultry and game birds. Hunting pressure in these regions can reduce local populations, but the hunting rarely eliminates foxes entirely. Survivors recolonize quickly from surrounding areas. Legal protections vary too. Some regions classify foxes as protected wildlife. Others allow year-round hunting without limits. These different management approaches create a patchwork of conditions across the fox's range. But even in areas with minimal protection, foxes persist. Their reproductive capacity and behavioral adaptability keep populations stable despite human pressure. The fur trade once threatened fox populations in some areas. Historical trapping for pelts removed large numbers of animals from wild populations. Modern fur farming reduced trapping pressure, though it created animal welfare concerns of different kinds. Currently, the fur trade has minimal impact on wild fox populations in most regions. Fashion shifts and ethical concerns reduced demand for wild-caught fur. Success stories exist across the fox's range. Populations in areas where they were once rare have recovered. Urban colonization created new habitat where none existed before. Some regions report increasing fox sightings after decades of decline. These positive trends suggest the species is not just surviving current changes, but finding opportunities within them. Research continues revealing new aspects of fox biology and behavior. The magnetic hunting discovery happened in 2011, less than 15 years ago. Before that, we had no idea foxes could sense magnetic fields. What else might we be missing? What other sensory capabilities or behaviors remain undocumented because we haven't thought to look for them? Young researchers entering wildlife biology bring new questions and new technologies. GPS collars that track movements with meter-level precision. Camera traps that document behavior without human presence. Genetic analyses that reveal population structure and adaptation in detail impossible a generation ago. Each technological advance opens new windows into understanding how foxes live and how they're responding to rapid environmental change. The fox watching us from the edge of the woods carries within it millions of years of evolutionary history. Adaptations refined across countless generations, instincts that guided its ancestors through ice ages and warming periods, but it also carries something more recent. Learned behaviors acquired within its own lifetime, knowledge of where food appears, which sounds indicate danger, how to navigate a world increasingly shaped by human activity. That combination of ancient instinct and rapid learning makes the fox resilient in ways many species are not. It can call on deep evolutionary adaptations when needed. The magnetic hunting, the night vision, the seasonal coat changes, but it can also learn new tricks. Urban navigation, traffic pattern recognition, novel food, source exploitation. This dual capacity for both instinctive and learned behavior positions the fox well for an uncertain future. The years ahead will test that flexibility. Temperatures will continue rising. Weather patterns will keep shifting. Human populations will keep expanding into remaining wilderness. And through all of this, the fox will face choices: where to hunt, where to den, whether to stay in traditional territories or move into new areas as conditions change. We can't predict exactly how these choices will play out, but if history offers any guidance, the fox will adapt. It always has. Through every challenge evolution or humanity placed before it, the fox found answers, found ways to survive and even thrive when conditions should have pushed it toward decline. That track record suggests the fox has more adaptations yet to reveal, more flexibility than we currently recognize. Night settles across the landscape. The fox emerges from its den and begins another hunt. The same behavior its ancestors performed for thousands of generations, the same instincts guiding its movements through darkness. Tomorrow will bring new challenges, new changes in the world it navigates, but tonight is for hunting, for living the life evolution shaped it for being the magnetic hunter that learned to see in darkness, that learned to thrive in cities and survive in deserts, The fox continues forward, adapting, surviving, thriving, and we're privileged to witness it. Chapter 11. Evening arrives gently. The sun drops toward the horizon, painting the sky in shades of amber and rose. Shadows lengthen across meadows and streets. Temperature begins its slow descent from day's warmth into night's coolness. And somewhere between light and darkness, in that quiet hour when the world transitions from one state to another, the fox stirs. The den entrance shows the first signs of movement. A nose appears, testing the air. Reading the evening through scent carried on gentle breeze, then ears, rotating slowly, listening to the soundscape that will define the next several hours. Finally, the whole fox emerges, stretching, shaking, preparing for the night ahead. This moment repeats itself across the northern hemisphere, in forests and deserts, in cities and wilderness. Thousands of foxes waking to the same quiet call that has pulled them from dens for countless generations. The instinct is older than memory, deeper than thought. It simply is. The fox moves through familiar territory, each tree recognized, each rock remembered. The landscape exists as much in memory as in present vision. You could walk this path in complete darkness and know where every obstacle sits, where the ground dips, where the trail narrows between bushes. Knowledge built through repetition, through traveling the same routes night after night, until the territory becomes extension of self. Hunting begins without announcement. There's no moment when the fox decides to start. It simply transitions from traveling to hunting. Movements become more deliberate, pauses lengthen, attention sharpens. The fox reads its environment constantly. A sound from tall grass, movement detected in peripheral vision, scent carried on wind, each input processed, evaluated, most dismissed. Occasionally, something registers as worth investigating. A mouse moves beneath snow. The fox tilts its head, listening, calculating. The magnetic sense activates without conscious effort. Alignment happens naturally. The fox adjusts position slightly, finds the angle that feels right, then launches upward. The arc through cold air, the penetration through snow, and emergence with prey secured. Sometimes the strike succeeds, sometimes it fails. Both outcomes are part of the process. The fox doesn't dwell on failure, doesn't celebrate success. It simply continues. The next opportunity will come, or it won't. Either way, the night continues and the fox moves through it. Hours pass in this rhythm. Hunt, travel, rest briefly, hunt again. The pattern flows without forced urgency. Food will appear or it won't. Stress serves no purpose. The fox operates in a state we might call presence, fully engaged with the immediate moment, not thinking about yesterday's hunt or tomorrow's weather, just here. Now, this scent, this sound, this moment of existence. Other foxes move through neighboring territories. Paths cross occasionally. A brief acknowledgement. Scent marking to reinforce boundaries. Sometimes a vocalization. Usually just recognition and separation. Lives run in parallel without intersection. Each fox in its own space, pursuing its own needs. Connected by species and proximity, but fundamentally solitary in the execution of life. The moon rises, light changes, shadows shift from one configuration to another. The fox notices but doesn't analyze, it adapts automatically to changing visibility, adjusting hunting techniques, modifying approach strategies. Flexibility built so deeply into behavior that it operates below conscious awareness. Clouds move across the moon. Darkness deepens. For humans, this would be disorienting, but the fox sees through its tapetum lucidum, the world remains visible, less detailed perhaps than in full light, but navigable, sufficient. The darkness that blinds us is merely dimness to the fox, not obstacle, just another condition to move through. Prey appears, the fox approaches. The magnetic sense guides distance calculation. The specialized skull shape prepares for impact. The shock-absorbing paws ready for landing forces. All these adaptations working together without thought, without planning. They simply function, as they've functioned for thousands of years, as they'll function tomorrow night and the night after. The catch happens, or doesn't. The cycle continues, energy expended, energy gained. The balance that defines survival, playing out in real time. Most nights balance roughly even, some nights tip toward deficit, occasionally toward surplus. Over time, across weeks and months, the fox maintains equilibrium. Enough success to sustain life, not so much failure that survival becomes impossible. The night deepens toward that darkest hour before dawn, when even artificial lights dim, when cities sleep and forests rest in profound stillness. The fox continues hunting, its night is long. Sleep will come later, when morning brightens the eastern sky, when diurnal creatures wake and nocturnal hunters retire, when the shift changes and the fox's time on stage concludes. But that's still hours away. For now, there's only the present, this moment, this meadow, this possibility of prey hidden beneath snow or grass. The fox walks forward, patient, persistent, carrying within itself all the adaptations we've explored, the magnetic hunting, the night vision, the seasonal transformations, the learned behaviors, the ancient instincts, all of it present in this single animal moving through darkness, all of it functioning together to produce something elegant in its simplicity. A fox, hunting, living, being exactly what evolution and experience shaped it to become. The wind shifts, carries new scents. The fox pauses, processes information, decides on a new direction, turns, continues. The night holds more hours yet, more opportunities, more moments of existence to experience and navigate. The fox doesn't hurry, doesn't delay. It simply moves at the pace that feels right, that balances energy conservation with hunting necessity. That works. Somewhere in a distant city, another fox moves through alleys between buildings. Its night looks different, smells different, sounds different, but the essential experience remains similar. Movement through territory, search for food, navigation of familiar space. The urban fox and rural fox living separate lives that share fundamental patterns, variations on a theme that persists across diverse environments. And in the desert, another fox emerges from its den into cooler night air. Relief from day's heat. Time to travel to water sources, to hunt, to maintain territories and social connections. Same species, same instincts, different landscape requiring different specific behaviors, but the underlying drive's identical: food, water, survival, reproduction. The basic requirements that unite all foxes regardless of where they live. The night continues its slow progression toward dawn. The fox continues its movements through darkness. Nothing dramatic happens. No crisis emerges. Just the steady accumulation of small actions that collectively constitute a life. A hunt here, a cache there, a moment of rest, a response to distant sound, minutes flowing into hours in a rhythm as old as the species itself. This is what survival looks like. Not epic struggle, not constant drama, just persistent engagement with the world, showing up night after night. Doing what needs doing, adapting when necessary, maintaining patterns when possible, the fox as it has always been, as it continues to be, as it likely will continue being long after we've stopped watching. The earth turns, the night ages, the fox hunts, and in this simple continuation, in this persistent existence across changing conditions and evolving landscapes, we find something worth noting. The fox survives not through spectacular adaptations alone, but through the quiet competence of doing ordinary things consistently well, of being present, of adapting, of continuing. The magnetic hunter moves through its territory, guided by instincts we're still learning to understand, shaped by evolution and experience, carrying forward patterns that worked for ancestors and preparing to pass those patterns to offspring, a living link in a chain that extends into deep past and projects into uncertain future. Night holds the fox, and the fox holds night, the two inseparable, bound together in a relationship that defines both. Without darkness, the fox's adaptations mean less. Without the fox, the night is less fully inhabited. Together they create something complete, something that works, something that continues. And as we finish our observation, as we prepare to leave the fox to its hunting and its life, we carry with us new understanding of hidden senses, of unexpected adaptations, of flexibility and persistence. The fox gave us these insights, allowed us to glimpse how one species navigates a changing world with grace and capability. The hunt continues, the night deepens, and the fox, that magnetic hunter in darkness, moves forward into whatever comes next. The forest breathes in night's embrace. Trees stand silent under starlight. A stream moves over stones with the same rhythm it held yesterday and will hold tomorrow. Everything continues as it has, as it will. Time moves through this place without urgency, without announcement. Just the slow turning of hours into darkness and darkness into dawn. The fox has returned to its den. The night's hunting complete. Energy gained balances, energy spent, not perfectly, never perfectly, but close enough. Tomorrow will bring another night, another opportunity to balance that equation again. For now, rest calls with gentle insistence. Morning light touches the horizon. The sky shifts from black to grey to pale blue. Birds begin their dawn chorus, tentative at first, then building into full voice as light grows. The forest wakes to a new day, but the fox sleeps through this transition. Day belongs to others. Squirrels emerge. Deer move to feeding areas. Songbirds work through territories. The fox's world rests until darkness returns. Hours pass in stillness. The sun climbs. Shadows rotate around the den entrance. Temperature rises gradually. Inside, the fox remains motionless except for the gentle rhythm of breathing. In, out, the body maintaining itself, repairing, preparing, building reserves for the next active period. Nothing dramatic occurs during these daylight hours. No crisis demands response. No opportunity requires action, just continuation. The fox existing in a state between full consciousness and deep sleep, aware enough to respond if danger appears, relaxed enough to gain rest's benefits, a balance point that serves survival without demanding vigilance. The den holds this stillness. Earth surrounds and protects. Above, the world carries on with its daylight business. Below, the fox rests in darkness that comforts rather than threatens. This small space carved from soil and rock becomes universe entire for these hours. Nothing beyond matters, nothing outside requires attention, just here, just now, just rest. Afternoon arrives, the sun reaches its apex and begins descent toward evening. Light changes quality, shifts from harsh brightness to softer illumination. The fox stirs slightly, adjusts position, settles again into sleep. Not ready yet, not time yet. A few more hours of rest remain before the transition back to waking. This rhythm defines the fox's existence. Night for activity, day for rest. The pattern repeating endlessly. Each cycle similar to the one before. Variations occur. Sometimes the fox wakes earlier, sometimes later. Sometimes it emerges briefly during late afternoon, but mostly the pattern holds. Consistency that serves life's requirements without requiring conscious choice. Other foxes rest in other dens across the landscape, each in its own space, each following similar patterns. Lives running parallel without intersection, connected by species and instinct, but separate in execution. The fox in the city sleeps beneath a garden shed. The fox in the desert rests in a rocky crevice. The fox in the northern forest curls in an earthen burrow. All sleeping, all resting, all preparing for the night that approaches. Clouds drift across afternoon sky. Their shadows move over land. Temperature fluctuates slightly as sun appears and disappears behind white masses. Rain threatens but doesn't arrive. The air holds moisture without releasing it. Everything waits. Everything rests in the space between what was and what will be. The fox's breathing continues its steady rhythm. No dreams interrupt now, just deep sleep. The kind that erases awareness of time's passage. When the fox wakes, hours will have vanished. The afternoon that felt imminent when it last stirred will have aged into evening. Time compressed through the simple act of sleeping. This is survival's quiet side. The unglamorous hours. No hunting, no navigating, no problem solving, just basic maintenance, the body repairing itself, energy stores rebuilding, the nervous system resetting for another active period, essential work happening without consciousness directing it. Automatic processes refined through evolution to work efficiently without oversight. Light begins its slow fade toward evening. The quality changes again, softens further, takes on the golden tone that precedes sunset. Birds shift from afternoon feeding to evening calls. Their voices different now, more melodic, less urgent. Even they sense the transition approaching. The fox stirs again, more definitively this time. Eyes open briefly, close again. Not quite ready, but awareness returns gradually. The deep sleep lifting, replaced by lighter rest that permits consciousness to emerge when the moment arrives. Soon, but not yet. A few more minutes of rest remain. Inside the den, temperature stays constant. The day's heat barely penetrated this deep. Night's approaching cold hasn't arrived yet. The fox exists in stable conditions, comfortable, protected, safe. This den represents security earned through knowledge. The fox learned where to dig, how deep to excavate, where to position the entrance for optimal drainage and temperature control. Knowledge applied successfully. Sunset approaches. The sky transforms through its evening palette. Orange, pink, purple. Colors shifting and blending as light fades. Stars begin appearing in the darkening east. The moon rises, already visible against twilight blue. Everything moves toward night with steady inevitability. The fox uncurls, stretches within the confines of the den. Muscles awakening after hours of stillness. The body checks itself. Everything functional, everything ready. The transition from rest to activity begins internally before any external action occurs. Systems activating, awareness expanding. The fox preparing to engage with the world again. But there's no rush. Never rush. The night holds many hours. Prey will be available later, as easily as now, perhaps more easily after darkness deepens and prey species begin their own nocturnal activity. The fox learned patience long ago, learned that waiting often produces better results than hurrying. So it sits inside the den entrance, watching evening deepen, listening to the soundscape change as diurnal creatures, quieter nocturnal ones, wake, the world shifting between two states, day world ending, night world beginning. The fox inhabits that transition, belongs to it, has evolved specifically for the interface between light and darkness. The first stars shine clearly now, Venus bright in the west, the moon climbing higher, twilight fading into true darkness, and the fox steps from its den, begins another night, another cycle, another iteration of patterns that have worked since before memory began. The forest receives the fox back into its nocturnal world. The meadow welcomes its magnetic hunter. The city acknowledges its adaptive survivor. Wherever the fox emerges, it belongs there, has earned its place through competence and persistence, through showing up night after night, through doing what needs doing without complaint or drama, and we, having followed the fox through its nights and days, through its adaptations and behaviors, through its challenges and successes, can step back now. Let the fox return to being simply fox, unobserved, unprofiled, just an animal moving through its life with the quiet excellence that characterizes its species. The magnetic sense guides when needed. Night vision reveals what darkness hides. Seasonal coats adjust to changing temperatures. Vocalizations maintain social connections. Caching stores surplus against future need. All these adaptations working together, creating something complete, something that functions, something that persists. The fox represents possibility, shows us that adaptation need not be dramatic to be effective, that flexibility matters more than specialization in changing times, that learning can happen fast enough to matter, that ancient instincts and modern challenges can coexist within a single life successfully navigated. We carry these lessons forward, apply them or not as we choose. The fox doesn't teach deliberately, it simply lives. But in that living, in that persistent engagement with existence, it demonstrates principles worth noting, worth remembering, worth applying to our own navigation of uncertain futures. The night deepens around the hunting fox, stars wheel overhead, the moon climbs toward zenith, hours unfold in their measured pace, and the fox moves through them, patient, capable, present, being exactly what it is, nothing more required, nothing less possible. This is where we leave it, the fox in its element, the night embracing its hunter, the world continuing its ancient patterns. We've witnessed something profound disguised as ordinary, survival not as dramatic struggle but as quiet competence, excellence not as exceptional achievement but as consistent showing up. The forest holds its fox, the desert cradles its survivor, the city houses its adapter, each fox in its place, each place shaped by its fox, the relationship mutual, reciprocal, neither complete without the other. And in this completion, in this fitting together of animal and environment, we find something that transcends both. The fox continues forward, always forward, into the night that rises to meet it, into the hours that hold possibility and challenge in equal measure, into the future that remains unwritten but approaches with each passing moment. The fox doesn't fear this future, doesn't anticipate it, simply meets it as it arrives with the same patience and competence that served its ancestors, that will serve its descendants, that serves it now. And as the night settles fully, as darkness becomes complete. As the fox disappears into the landscape it knows so thoroughly. We release our observation, let the fox return to privacy, to the unwitnessed existence it lived before our attention arrived. We've learned what we came to learn, seen what we came to see. Now the watching ends, the forest breathes in, the fox hunts, the night holds both. And in this holding, in this ancient dance of predator and darkness, of adaptation and environment, of persistence and change, we find something worth preserving, worth protecting, worth allowing to continue into whatever future awaits. The story ends here. But the fox's story continues, will continue tomorrow night, and the night after, and for all the nights stretching forward into time we cannot see. The magnetic hunter endures, adapts, survives, lives, and that perhaps is enough. The quiet hours return, the fox to its hunting, the world to its turning, and we to our rest, having witnessed something ancient and ongoing, something that preceded us and will likely outlast us, something simple and profound, a fox moving through darkness, living as it has lived, as it will live, as it must live. The night receives all this without judgment, holds the fox and its hunting, holds our observation and departure, holds everything that happens within its hours with equal acceptance. And in this acceptance, in this quiet holding, we find peace. The fox hunts on, the night deepens, and somewhere between the two, in that space where animal meets environment, where adaptation meets challenge, where ancient meets modern, the red fox continues writing its story, one night at a time, one hunt at a time, one quiet moment of competent existence at a time. And so we rest now, having learned, having witnessed, having understood something that words struggle to capture but experience reveals clearly. The fox is the fox, the night is the night, and together they create something worth knowing, worth protecting, worth allowing to continue its ancient patterns into whatever future unfolds. Sleep comes easily after such observation. The mind settles, the body relaxes, and in the darkness behind closed eyes, perhaps we dream of foxes hunting,